Hi everyone. In this video we're going to be talking about chemistry or the chemical level of organization, and we mentioned previously that the chemical level of organization refers to atoms and molecules that basically form the basic structures of the human body. And so in this video we're going to start to introduce some vocabulary that we need in order to talk about what's happening at the chemical level. Now, one disclaimer that I'd like to offer is that the amount of chemistry that we're going to cover in these videos is the minimal amount necessary to appreciate what's happening in the human body, but there are going to be some oversimplifications and things that aren't quite representative of the whole subject of chemistry. So the first thing we want to talk about is matter. Matter is anything that takes up space and has mass. And mass is a measure of how much matter is in a particular object. Now, one point that I want to make is that mass and weight are not the same thing. Weight is mass times gravity. So if we're considering standing on a scale, how much we weigh, it's taking into account how much of us there is in addition to the gravitational pull of the Earth. And a good comparison would be if you went to the moon, you would weigh less than you would on Earth, but your mass, the amount of you, would still be exactly the same. There are three types of matter that we want to discuss. They are solid, liquid, and gas. And something can exist in each of the states of matter. So, for example, if we think of ice in the solid state, it's equivalent to water in the liquid state and steam in the gaseous state. Now, in terms of the human body, things that exist in the solid state are things like proteins and cell membranes. Examples of liquids are body fluids such as blood, urine, saliva. And then things that exist in the gaseous state are things like oxygen and carbon dioxide, the gas that we breathe in, the gas that we exhale. The next thing we want to discuss is the atom, which is the smallest stable unit of matter. And it's comprised of three subatomic particles. The subatomic particles are protons, which have a positive charge associated with them, neutrons, which are neutral or have no charge, and electrons, which are negatively charged. Now, the magnitude of the proton positive charge and the magnitude of the electron negative charge are equal. So one positive charge of a proton will cancel out one negative charge of an electron. The protons and the neutrons are similar in mass and size, but the electrons are much lighter than both the protons and the neutrons. So let's take a look at the atomic structure. We'll use P+ to represent the proton, we'll use N to represent neutron, and E- to represent the electron. So just the letter and then the charge that is or is not associated with it. And we'll use some color coding scheme as well. So if we draw the protons and the neutrons, they'll be together in what's called a nucleus. And typically, the number of protons will equal the number of neutrons, but there are examples of when the number of neutrons will vary slightly, and there'll be a few more or a few less than the number of protons. Now, the electrons will surround the nucleus, and the sort of original model that was considered, it suggested that the electrons were in orbit around the nucleus, similar to the moon orbiting around Earth. But that's actually not quite accurate. We're going to draw it that way for simplicity. But in all reality, the electrons are sort of contained in electron shells, and the electron can be found sort of anywhere in that area. So it could be actually much closer to the nucleus than we've drawn it. It could be a little bit further from the nucleus than we've drawn it. It's not actually in orbit. Now, one thing that we should note is that the nucleus is positively charged because of the presence of the protons, and the electrons we know are negatively charged. And the positive charge associated with the proton is going to attract the negative charge associated with the electron. I like to use the comparison of magnets. So magnets have typically a north pole and a south pole. And we know that when you have two magnets that are in really close proximity, if you have them oriented, so we have the South Pole and the North Pole facing each other, they will attract, and we'll see the magnets sort of suck together and then stick. But conversely, if you were to take one piece of the one magnet and turn it around so that the North Pole and the North Pole were facing each other, or conversely, the South Pole and the South Pole are facing each other, or if we were to take a positive charge and a positive charge and bring them together, or a negative and bring them together, we would know that they would repel each other. So if you take the opposite ends of the magnet, they'll attract, but if you take the same ends of the magnet and try to push them together, they'll repel, and it will be really difficult to try to hold them together. So we can determine that opposite charges will attract and like charges will repel. And so it's really important to note that because we have the positive charge in the nucleus and the negative charge in the electron surrounding the nucleus, the electron will stay in relatively close proximity. It's constantly moving, but it wants to be associated with that nucleus. Now, when we think about different types of atoms, we can note that there will be different numbers of protons and different numbers of electrons, and so sometimes we'll have more than one electron shell as we've originally drawn. So the outermost shell will be called the valence shell, regardless of the number of shells that there are, but there will always be at least one shell unless we talk about just one proton all by itself, which there'll be a few times where we have to mention that. But there'll usually be at least one shell, and then the number of electrons will determine how many additional shells. So in this particular drawing, we now have 2 shells, and the outermost shell is considered the valence shell. If we were to draw a third, the first and the second would just be electron shells, and the third would be considered the valence shell. Now, one thing I want to mention is that the protons, the number of protons that are present in the nucleus, is what determines the atomic number of that particular atom. And so we can have different atoms that have different numbers of protons, and we just differentiate them by saying, okay, if this particular atom has 7 protons, then its atomic number is going to be 7. If the next one that we look at has 8, its atomic number is going to be 8. The number of protons is also equal to the number of electrons in its normal basic state, and we'll talk about some variations of that, but generally the number of protons equals the number of electrons. So if you know that, say, the atomic number is 7, we know that there are 7 protons, and we also know that there are 7 electrons associated with that particular atom. The electrons are organized into the electron shells, and they follow a very specific pattern. So for example, in this drawing, we only drew 2 electrons in the first shell. The first shell only has a capacity of 2 electrons. The second shell has a capacity of 8, and the third shell has a capacity of 18, although we're actually going to sort of focus on the third shell only a couple of times, and we'll sort of say that the atom is happy if it has 8. So we're going to sort of deviate a little bit from getting into the depth of the chemistry here, and we're just going to be comfortable with 8, and I'll kind of explain that in a later video. So the electrons that are in the valence shell can interact with other atoms. So they're the ones kind of around the outside. They're the only ones that can kind of like look around and see if there's any other atoms that they can hang out with or play with or interact with. And all the atoms that are in the inner shells really don't have the ability to interact. So we mentioned that the valence shell has a maximum number of electrons that it can hold. If it's holding all of its electrons, it's considered stable. It's actually very happy. But if there's an unfilled valence shell, meaning that it doesn't have the maximum number of electrons, it's considered unstable. And unstable atoms are likely to interact with other atoms, whereas stable atoms like to really hang out by themselves. So we're going to talk more about that. But first, let's talk a little bit about elements. So elements are basically classifications of atoms based on their atomic number, which we also know is based on the number of protons that exist in the atom. And the elements are organized in what's called a periodic table. So I'm going to try and draw a periodic table. It's going to be more of a cartoon version, and I'm not going to fill in the entire table. So really just want to give you an idea of what it looks like and highlight a couple of important features of the periodic table. In particular, I'm going to fill in the elements that it's important that we know for the purpose of studying the human body, and all the rest of them that are left blank are ones that we don't really need to know. So you can certainly just Google search a periodic table and get an idea of what it looks like in completion. And there's some periodic tables are more simple and have just the amount of information that I'm going to include, and some periodic tables are more complex. They'll be color coded, and they will also provide additional information such as the atomic weight. All right, so let's fill in our periodic table with some of the elements that we want to take a look at. So starting from the upper left, we have hydrogen, which is atomic number 1, and that means that hydrogen has 1 proton, and it also means that it has 1 electron. All the way to the right, we see helium, And helium is atomic number 2, so it has 2 protons, and it also has 2 electrons. And then we'll start numbering again from the left and just sort of number across. So as I mentioned, I'm not going to fill in the entire table, but in the second row, we have 3 and 4, and then we skip over to the other side and we receive 5, 6, 7, 8, 9, and 10. So I'll fill in 6, which is carbon, 7, which is nitrogen, 8, which is oxygen, 9, which is fluorine, and 10, which is neon. Next row, we see number 11, sodium, number 12, magnesium, 15, phosphorus, 17 is chloride, 18 is argon, and then the fourth row, potassium, which is number 19, number 20, calcium, number 26, iron, which is Fe, and then we'll skip down to the fifth row and we see iodine, which is number 53. So I've been referring to the periodic table in the context of rows. The rows actually, the proper term for that is period. So if we consider one row, we would actually call it period. So I'm going to number on the side 1, 2, 3, 4, 5, 6, and 7. So the number 1 in green represents the first period. The 2 represents the second period, and so on. And then if we consider the columns, we actually refer to those as groups. I'm not going to number the groups, but there are some similarities in terms of the features of a particular set of elements that are in the same group. One example of that is the noble gases. So we notice that helium, neon, and argon in blue have 2, 10, and 18 electrons respectively, which means that they have a full valence shell. So it actually turns out that these are noble gases. Every element in this column has a full valence shell, and those elements are very stable and they don't want to interact with any other atoms. So let's consider another element. Let's consider sodium. And when we consider sodium, we're going to actually draw the electron configuration of sodium in sort of a two-dimensional format. Now, this is an oversimplification of how the electrons are actually organized, and this doesn't really give you a full picture, but it's going to help us to keep track of the electrons. So we're going to use this method of drawing, at least for now, and for the purpose of discussing chemical bonding. So we know that sodium, number 11, has 11 protons and therefore has 11 electrons. So we're not going to draw the nucleus, but we'll draw a little Na in the middle, and we'll assume that there are 11 protons in there. And then we're going to draw the 11 electrons around the outside. So we mentioned before that the electrons are organized in shells, and the first shell can hold 2 electrons, the second shell can hold 8. That makes a total of 10. What that means is that in the third shell, or the valence shell, we're going to have 1 lonely electron. So in the case of sodium, there are actually 7 other spaces for electrons, but there really is only 1 electron that's on the outside, and that lonely electron actually makes this particular atom very unstable, and it wants to interact with other atoms. So anything that's unstable will want to interact with other atoms, and it would like to form a chemical bond. So we're going to talk about chemical bonding in the next video. So before we get too ahead of ourselves, I just want to write out all the elements that are found in the human body that we mentioned in the periodic table, and associate their symbol with their actual name, because if you notice, some of them are not, they're not really that obvious. So H refers to hydrogen, C refers to carbon, O refers to oxygen, N is nitrogen, P is phosphorus, Na is sodium, Mg is magnesium, K is potassium, Ca is calcium, Cl is chlorine, I is iodine, Fe is iron, and then I'm just going to also draw over here. These are not typically found in the human body, but I just want to mention them. These are the noble gases that we were mentioning before. He is helium, Ne is neon, and Ar is argon. So it's really, really important for the sake of particularly the ones in purple for the human body that we're able to know not only the symbol but also the name, because we're going to refer to these elements quite frequently, especially in the next couple of lectures. All right, so lastly, I want to just mention molecules and compounds, because it sort of wraps up our introduction to terminology that we need to discuss chemistry. So molecules are two or more atoms that are bonded together. This could be two atoms of oxygen to make O2. This could be two atoms of hydrogen to make a hydrogen molecule. And it could also be H2O, two atoms of hydrogen, one atom of oxygen to make water. We'll compare that to compounds. Compounds contain two or more elements. Two or more elements are involved in making the chemical bond. So H2O is an example of a compound because it contains hydrogen and oxygen, but H2 and O2 are not considered compounds because they're only using one element, just more than one atom of one element to make that particular molecule. So those are not considered compounds. So I'm going to write a couple of notes about that here, and I do this because oftentimes when I'm teaching, students will ask this question. I don't think it's important that you memorize these statements, but for some people it might be helpful. A compound is always a molecule, but a molecule is not always a compound. I don't like these things because I think that it kind of gets confusing and then it's hard to remember which is which. I think you just think of compound, like if you think of a compound word, it's two words that are put together. So just kind of remember that that means, in this case, two elements that are put together. And I think that will serve you just fine. One other point that's critical about compounds is that when a compound forms, it may display new chemical properties, and we'll be able to talk about that a little bit more in a later video. Let's just quickly recap some of the things that we learned in this video so that we can prepare for a discussion on chemical bonding. So we can see a nucleus that contains a combination of protons and neutrons. In this case, it'll be 7 protons and 7 neutrons, and then around it we'll draw our electrons in their respective shells. So if there are 7 protons, that means that there can be a maximum of 7 electrons. So we'll draw 2 electrons in the first shell and then 5 electrons in the valence shell, making a total of 7. So we know that the atomic number is 7, and since the atomic number is 7, we know that it's also an atom of nitrogen. And we also know that the valence shell for nitrogen is not full. Since it's not full, we'll consider it to be unstable, which means that it wants to form a chemical bond in order to achieve stability. So nitrogen has 3 spaces left, and nitrogen can actually interact with other atoms to sort of fill in those spaces, and that's what we're going to focus on in our next video. So I hope you enjoyed it. Thanks for watching.